It seems like our theories do not align with the real observations of the universe. Let's make them align. Let's include some matter. We won't have any idea what it is, but let's make it 5 times more than everything we currently observe in the universe. I think that's how some people envision the concept of dark matter. And to be honest, that's not far from the truth.
Well, if you put it like this, it becomes clear why quite a few people enjoy arguing about dark matter.
I'm mostly talking about regular people and not the scientists. And on the internet, I often come across haters of dark matter.
And the question is valid. Isn't it too much to introduce into the model of the universe some mysterious invisible substance which is even more abundant than the ordinary matter that makes up planets, stars, and everything we see around, only to make the theories about the universe align with what we actually observe? Well, if it were just someone's random idea explaining, for instance, one aspect of the observable universe but failing to explain all the rest, then the answer to the question would be yes. But the thing is, dark matter explains not just one aspect of the universe, but several independent aspects.
At the same time, it doesn't mean that the concept of dark matter is without its problems.
Take, for example, the fact that more than 90 years after the term dark matter was first coined by Fritz Zwicky and the idea of dark matter was born, after decades of attempts to detect dark matter particles on particle detectors, if we specifically are talking about dark matter as some unknown particles. Despite the fact that these detectors have become orders of magnitude more sensitive, we still haven't found any signs of dark matter particles, and to this day we still don't know what it really is. This doesn't mean they don't exist. It's entirely possible that next year or in next 50 years we will discover promising candidate particles. However, we have been trying for quite a long time, and therefore,
and actually not just because of that. Some scientists have considered, what if dark matter is a mistake? Perhaps there is some other, better explanation for the discrepancies between theories and observations. Well, maybe there is.
Dark matter is still considered the most likely explanation today, and the majority of astrophysicists can probably be considered proponents of this idea.
But still, science is not about majority opinion, and not about blind belief as some might think. If an alternative arises that works better, it can replace the old theory.
Is there anything that could dethrone the idea of dark matter? There are alternatives, some are not even new, while others have emerged quite recently in the last few years.
Once I was scrolling through feeds of press releases for scientific articles and I came across this headline.
Dark matter. Our review suggests it's time to ditch it in favor of a new theory of gravity.
It does sound quite sensational.
This article briefly covers a large review, the full text of which spans almost 150 pages. And this article prompted me to delve deeper into this topic. Is it really time to abandon dark matter? What are its problems and what do alternative theories propose?
Today we will talk about all this and more. My name is Andrei, and this is Cosmos Elementary.
Dark matter, a mysterious substance, the mass of which in the universe, according to current estimates, is more than 5 times greater than the mass of baryonic or ordinary matter. It constitutes approximately 27% of the total mass energy of the universe. A substance that likely doesn't emit, reflect, or absorb any light or radiation, and in general appears to interact with ordinary matter only through gravity. It may even not interact with itself. It is often said that's why it's called dark, because it doesn't emit or reflect light. But then it would be more accurate to call it transparent rather than dark. Sometimes it is said that by dark we mean we don't know what it really is, which is true. We have no idea. There are theories that dark matter consists of unknown particles beyond the standard model. Scientists are trying to detect either these particles or signs of their presence using specialized detectors. Less popular theories suggest that ordinary matter, which is simply hard to detect, could play the role of dark matter. For example, lots of faint brown dwarfs or black holes.
Let's start by briefly refreshing our memory and going through main arguments in favor for the existence of dark matter. As I've mentioned before, it's not just someone's random idea, and evidence in favor of dark matter has been accumulating for decades.
Many arguments are based on our current understanding of gravity. We have a pretty good idea of how bodies move in space on certain scales. Knowing masses and velocities of objects in a system, as well as the distances between them, allows us to describe and even predict their motion. Or conversely, not knowing some of these parameters, by observing bodies, we can calculate those unknown parameters. For example, by observing the orbits and motions of two massive bodies, we can calculate their mass. One depends on the other.
In some cases, Newtonian mechanics is enough, while in others, it's better to consider the effects of relativity.
For instance, the unusual behavior of Uranus on its orbit, the oscillations of its orbit, led to the conclusion that there might be another planet beyond the orbit of Uranus, causing those perturbations. This turned out to be true, leading to the discovery of Neptune. But Newtonian mechanics was not sufficient to explain the precession of Mercury's orbit. In the end, Einstein's general theory of relativity proved to be the solution here.
So the behavior and motion of objects in space can lead to new discoveries.
So when we look at the behavior of bodies in the solar system, it all seems to be working as expected. But then, when we go to larger scales, that's where things get interesting but weird. That's precisely what Fritz Zwicky did back in 1933. He observed Coma cluster of galaxies and measured the velocities of galaxies within the cluster, and found that they were moving fast. Too fast. It turned out that the visible mass of galaxies seemed to be not enough to hold these galaxies together. Planets do not escape from the Sun because they are not moving fast enough. However, if they were accelerated to a required speed, they could escape and overcome its gravity. So in this case, the velocity of these galaxies seemed to be high enough for them to fly away in different directions, but the cluster didn't disperse. That's when Zwicky concluded that there must be some additional hidden mass holding these galaxies together. If we step down a level to the scale of individual galaxies, observations there are not entirely smooth either. One of the main arguments in favor of dark matter is the galaxy rotation curves. In short, if we look at the solar system, we see that the farther a planet is from the Sun, or from the concentration of the most mass in the system, the slower its orbital velocity. If we plot a graph where the distance from the Sun is on one axis and the orbital velocity is on the other, we would observe a direct relationship, and the curve on the graph would gradually go down. This seems logical and aligns well with our understanding of gravity. A spiral galaxy at a first glance resembles a solar system, but on a much larger scale. However, in our galaxy, there is not just one central object. While there is a supermassive black hole at the center, all the stars in the galaxy don't orbit it in the same way planets orbit the Sun. It's a common misconception, and I've also covered this in a separate video. Nevertheless, a significant portion of the mass is concentrated in the center, and it's more correct to say that stars orbit around the center of the galaxy, rather than specifically around the black hole, even though it resides at galactic center. But whether it is one massive object or a concentration of mass from many objects, it was still expected that the farther a star is from the center, the slower its orbital velocity should be, just like for the planets in the solar system. However, measurements of stellar velocities in the Andromeda galaxy made by Vera Rubin in 1970 showed that it is not the case. The velocity of stars, as we go farther from the center, don't decrease. On the contrary, they initially rise and then level off, remaining roughly at the same level. And the rotation curves of many galaxies are flat and not declining as expected. Of course, they vary among different galaxies, and there is much more interesting information associated with these rotation curves that we will come back to. But the main point is that it's completely unclear why the velocity doesn't decrease. And this can be explained by additional hidden mass. And currently it is considered that the main mass of galaxies is not in the form of stars and gas, but in the dark matter halo that surrounds the galaxy. Moreover, considering the observed velocities, without dark matter, many galaxies should essentially disperse, similar to galaxy clusters. The fact that the stars are still held together is well explained by dark matter, whatever it may be.
Another important argument is gravitational lensing.
The general theory of relativity tells us that mass warps space-time itself, and that's what we call gravity. And photons follow these curved trajectories. This has been repeatedly confirmed by observations on different scales from the Sun to galaxy clusters. Mass acts as a lens and can focus and distort light coming from distant objects. Telescopes capture numerous images of distorted and even multiplied images of distant galaxies. So once again, the visible mass of galaxies in the foreground is just insufficient to explain the observed effects of distortion. Observations of gravitational lensing effects help create maps of distribution of dark matter and even estimate its mass. In this image, the distribution of mass, which could be dark matter, is shown in blue.
Another one of the main, if not the main, pieces of evidence in favor of dark matter is the bullet cluster. More precisely, it is the aftermath of the collision of two galaxy clusters which we observe.
So it goes like this. Let's take a galaxy cluster. What does it contain? Right? Galaxies. But besides galaxies, if we talk about ordinary matter, there's also intergalactic gas. And in terms of mass, it's actually much more. Many times more. When two such clusters collided, the galaxies, which are quite far apart from each other, simply passed by without colliding. However, when two massive concentrations of gas collided, they slowed down and heated up. Due to this heating, the gas began to emit X-rays. Thanks to observations from X-ray telescopes, we can see where this gas is concentrated. In this composite image, the gas is shown in pink. We of course also see the galaxies. These two clusters are massive and should cause gravitational lensing effects, distorting the galaxies in the background. Considering ordinary matter, the most significant distortion should be behind these pink gas concentrations, because there the mass of ordinary matter is much larger than in the galaxies.
But when scientists looked at the lensing effects, they turned out to be much stronger not where the gas was, but rather where the galaxies were, although there is just not enough mass to explain the effect.
Apparently, there is once again additional invisible mass, dark matter. In other words, during the collision, the gas collided and remained closer to the center of the collision, while the galaxies and dark matter passed by. The main mass, which could be dark matter, is shown here in blue. We observe gravitational effects of mass. However, the visible mass is not sufficient to explain those effects, indicating the presence of invisible mass, aka dark matter.
Another important point is the cosmic microwave background radiation. We won't go into details right now, but in short,
I've shown before such maps of cosmic microwave background radiation, the earliest light of the universe that we can observe, and which began to traverse the universe when the universe became transparent to radiation. Before that, there were inhomogeneities in the universe, and these inhomogeneities essentially imprinted on the cosmic microwave background, which we now see as slight temperature fluctuations in the microwave background, shown here in different colors. The crucial point is that the nature of these fluctuations depends on the properties of the universe at that moment, including its composition and the amount of different substances in the universe. And the background radiation that we observe is consistent with the presence of dark matter, even with the proportions and quantity of it that we estimate through other means. This visualization demonstrates what the cosmic microwave background would look like if the proportions of ordinary matter, dark matter, and dark energy were different.
Another point is the large-scale structure of the universe.
In observations, we see galaxies gathering into clusters forming even larger structures like filaments and walls, and computer simulations that take dark matter into account effectively reproduce this structure. However, this alone doesn't prove anything, and there could still be issues with this as well.
Of course, these are far from all of the arguments, and there are nuances and details in the ones that I mentioned. However, now at least we can see why the idea of dark matter is so popular.
Dark matter explains not just one aspect of the universe, but several, and it does it so in a relatively simple way.
But not everyone agrees with this. If we see that the universe seems to lack mass, one might think that instead of inventing new mysterious invisible matter, it would be simpler to attribute the effects of missing matter to the objects made of regular baryonic matter.
Various faint objects such as brown dwarfs, red dwarfs were proposed for the role of dark matter, and also black holes. However, this idea is not very popular today. For example, observations with telescopes indicate that red dwarfs are simply not abundant enough to play the role of dark matter. Observation of gravitational microlensing effects also indicate a shortage of objects like brown dwarfs. But the main thing is that, for example, by studying the CMB, we can roughly estimate how much ordinary matter there should be in the universe for it to appear as we observe it. These estimates align with what we actually see in the universe, and the visible mass is clearly not sufficient to explain the effects currently attributed to dark matter. So the options that remain involve considering scenarios where dark matter consists of unknown particles. And there are quite a few candidates, such as WIMPs, weakly interacting massive particles, axions, and so on. But even after decades of experiments, we haven't found any confident particle candidates using special detectors.
This could already make someone doubt that these mysterious particles exist at all. One of the main alternatives to dark matter emerged even before modern experiments, and it goes like this.
As I mentioned, the need for dark matter arises from the fact that observations on certain scales do not align with our understanding of gravity. What if the issue is not that we can't see the majority of mass in the universe, but that gravity works differently or not exactly as we think?
Therefore, instead of adding dark matter, some scientists propose modifying gravity. Probably the most well-known and popular version is modified Newtonian dynamics, or MOND for short.
The initial concept was proposed by Mordechai Milgram in 1983.
The essence of the idea is that gravity may behave differently on different scales, and it depends on acceleration.
Here, it turns out that for large masses and small accelerations, the standard law of Newtonian gravity no longer works. Large masses and small accelerations are precisely the scale of galaxies, and primarily, this modification is intended to explain the anomalies of galaxy rotation. In MOND, classical formulas of Newtonian mechanics undergo slight changes. A parameter related to acceleration is added to them. The parameter, this new constant, can be adjusted in such a way that the same formula will work both on the scale of the solar system and successfully describe its dynamics, and also on the scale of galaxies. So if the old version of the formula caused the problem of galaxy rotation curves, then now we have a formula that successfully describes both, and we don't need to invent any mysterious dark matter.
What is simpler? Slightly tweak the formula, or add 5 times the invisible matter to the universe? But actually what is important is not what appears simpler or more natural, but rather how well a particular hypothesis describes the largest number of observations and effects, and also how often it makes successful predictions.
It is interesting that on the scales of galaxies, modified gravity works very well. It accurately describes the rotation curves of many galaxies, although it's worth noting that not all of them. Why aren't MOND theories dominant today? It's typically said that yes, MOND does reasonably well in describing galaxies.
Moreover, some scientists even argue that for galaxies, some versions of MOND work even better than dark matter. It also may address some problems which arise in a primary cosmological model with dark matter.
But as we recall, among the arguments in favor of dark matter, I mentioned not only the rotation curves of galaxies. When it comes to other lines of evidence, such as the dynamics of galaxy clusters, observation of the cosmic microwave background radiation and properties of the early universe, MOND doesn't fare very well.
Well, what's there to talk about then? Sure, the idea of MOND is interesting and quite simple, but if it doesn't handle everything as well as dark matter does, then why bother? In general, that's why it didn't become the dominant theory. However, some scientists are still captivated with the idea of MOND. And there are some valid reasons for that. As I mentioned before, MOND works better with galaxies.
Yes, adding dark matter solves the issue of stellar velocities in galaxies, but the distribution of dark matter needs some adjustment. The dark matter hypothesis doesn't predict the exact velocities of stars in galaxies. Rather, it is invoked to explain the observed phenomena post facto.
But MOND can predict some things that we observe.
The Tully-Fisher relation is an observed correlation between the mass of a galaxy and the velocities within it. Dark matter doesn't predict this relationship, but MOND does. There is a whole book, A Philosophical Approach to MOND, in which modified gravity is examined from the perspective of the philosophy of science. This book is actually cited by the authors of the study I mentioned earlier, which inspired me to create this video. So, in this book, several more arguments are presented.
For example, the problem of missing satellite galaxies.
And by the way, I made a separate in-depth video about this issue. But in short, much of our understanding today relies on computer simulations. For a long time, simulations suggested that large galaxies should have many more satellite galaxies than we observe.
And here, clearly something is wrong. Either with observations, or with simulations, or with both. There are various approaches to solving this problem, which I covered in my video.
And yes, we can adjust the models to match what we observe in reality, but too much fine-tuning in simulations with large number of variables may lead to loss of predictive power of those models, so a balance is needed in this regard.
But MOND predicts a smaller number of satellite galaxies, which better aligns with observations.
Another point mentioned in this book related to the satellite galaxies is that for some reason, satellite galaxies tend to align in a certain plane rather than being distributed entirely randomly. This is observed, for example, with our Milky Way and Andromeda galaxies. Dark matter doesn't predict this, but MOND does.
Next, from time to time I see news headlines that predict the death of dark matter. And some of the research is quite interesting.
Another prediction of MOND is the so-called external field effect, according to which the internal dynamics of a system depend not only on the mass of the system itself, but also on the gravitational attraction of all objects in the universe. In our case, if we talk about galaxies, the rotation speed of a galaxy or the speed of stars would depend not only on the mass of the galaxy itself, but also on how many galaxies are nearby. So, if such an effect exists, under other equal conditions, two identical galaxies, one being relatively isolated and the other having many neighbors, would rotate differently.
If such evidence were to be found in observations, it would again speak in favor of predictive power of MOND.
And several years ago, there was a study where scientists examined the rotation curves of 153 galaxies. They found that for relatively isolated galaxies, the rotation curve is flat, meaning that stars farther from the center do not slow down. On the other hand, if a galaxy has many neighbors, in such galaxies, the rotation at the edges does slow down. These observations align with the prediction of the external field effect supporting MOND, and dark matter theories do not predict such an effect.
The sample size of galaxies is not very large, and it would be great to check this on the larger number of galaxies. But the study is quite interesting.
One of the critical points against MOND is its inability to explain the properties of the cosmic microwave background radiation, which dark matter successfully accounts for. However, there have been studies where researchers were able in principle to describe and explain the cosmic microwave background radiation with MOND by using gravity fields that varied over time. Another point to consider is that astronomers have discovered galaxies in which stars move so slowly that, according to dark matter version, there should be no dark matter present. It can be explained by the fact that the galaxy had dark matter in the past, but then lost it. However, in some cases, MOND still better explains such galaxies. I mentioned the bullet cluster, which is believed to be one of the main pieces of evidence in favor of dark matter, so some consider it to be a problem for dark matter. The physicist, science communicator and also a YouTuber, Sabine Hassenfelder, wrote about this in a popular science article and also mentioned it several times in her videos and talks. Here the argument is that the speed at which two clusters collided was estimated to be 3000 km per second. However, in simulations based on dark matter, such rapid collisions almost never occurred. Then there were studies where the odds were slightly higher, at least not 1 in 10 billion, but still such an event remained quite unlikely. And the shift in the focus of gravity can also be explained in MOND. But one of the main problems with MOND is the scale of galaxy clusters. Here, modified gravity alone fails to explain the velocities of galaxies within clusters. Even when using MOND to describe their motion, the mass of ordinary matter still turns out to be insufficient. Here, the success seen in rotation curves is not replicated. However, even this can be addressed by adding invisible mass. And you might say, hold on, are you suggesting using dark matter again? But that's not the case. Here, in combination with MOND, as the missing mass instead of mysterious unknown particles, they propose using neutrinos. These are well-known particles which are challenging but possible to catch. And if one type of neutrino has the specific mass, they can play the role of the missing mass when trying to describe the dynamics of galaxy clusters using MOND. In general, one way or another, MOND can explain many things that are usually believed to be better explained by dark matter. This includes galaxy clusters, CMB, and even gravitational lensing. And here we come back to the Reveiw which I began with. There, the authors thoroughly analyzed various arguments, and they created these very illustrative tables. These two tables compare how well both in the standard cosmological model with dark matter and in MOND, observational data align with the theory. Along the vertical axis, there is an assessment of how good the agreement is. Starting from the top, there is excellent agreement, then works well, plausibly works, some tension, and strong disagreement. And along the horizontal axis, it represents how much one has to, let's say, twist and adjust the theory to make the observations align. From clear prior expectation on the left to having to add various assumptions to the theory to align the observations with data on the right. In these tables you can see many arguments that we discussed today, as well as some others. So here for MOND, the two bottom rows are completely empty. And in the right column, where assumptions need to be made, in MOND there are fewer such arguments. Authors even devised a scoring system to compare the two approaches, and according to their conclusions, MOND scored more points. Hence the bold headlines suggesting that it's time to abandon dark matter. According to the authors of the Reveiw, MOND is considered better and simpler. Nevertheless, we don't see scientists rushing to abandon dark matter. All of the arguments listed here were known before, and they were just compiled here. However, this is just one work from two scientists. Some agree that dark matter works better with fewer complications for certain observations, while MOND works better for others. Perhaps each has its own merits. Can they somehow both work? Or should they be somehow combined? Or maybe in the end, the third idea will emerge that can better handle everything at once. By the way, there are already candidates for this, for example, the hypothesis of superfluid dark matter, which emerged quite recently, and it may work better than both. But the hypothesis is still young. Perhaps we can discuss it separately someday. What conclusion can be drawn from this? Perhaps that we know nothing. Well, of course, I am exaggerating a bit, but still, we are far from a complete understanding of the universe. Yes, there are working hypotheses, with some having more proponents than others, but all of them are being explored by reputable scientists. Who knows, perhaps tomorrow a dark matter particle might be captured on a detector, or breakthroughs might occur in some other theories. Thanks for watching. List all of the sources are, as usual, down below in the description, and if you enjoyed the video, leave a like, comment, subscribe for more videos in future, and if you really enjoyed it, feel free to share it with your friends, family, and everybody else. Bye!